balance in design for greater efficiencies. Module 1. Global impacts of building and resource efficiency. Buildings have a large environmental impact. Increasing urbanization and affluence are causing a boom in buildings and related environmental costs. Urbanization refers to the population shift from rural to urban areas, the corresponding decrease in the proportion of people living in rural areas. Affluence is the state of having a lot of money or owning many things. What we are seeing increasingly is a society of private affluence and public squalor. Buildings use energy and water resources for construction and operations, resulting in significant greenhouse gas, GHG, emissions and water scarcity. Greenhouse gas emissions are emissions of greenhouse gases that cause climate change by creating a greenhouse effect in the Earth's atmosphere. Water scarcity can be defined as a lack of sufficient water, or not having access to safe water supplies. The construction and operation of buildings consume 36% of world energy consumption and generate 39% of the world's GHG footprint. The current global GHG emissions due to buildings is more than the GHG emissions from India and USA combined. And buildings are set to almost double in the next 20 to 30 years in emerging markets. Building stock is projected to grow significantly today. 55% of the world's population lives in urban areas, a proportion that is expected to increase to 68% by 2050. 35 billion square meters of floor space is expected to be built in the next 5 years. This is the equivalent of adding an entire New York City every 6 months. Most of this growth is going to be in emerging markets. The chart below 2 shows the projected new building stock by country over the next years for some major emerging markets. Energy use in buildings. Electricity is the most popular energy type and its use is projected to increase. World energy consumption by sector and type. Buildings used 36% of the global energy use in 2018, with a majority of it being used in the residential sector. Energy consumption in buildings is projected to grow by 37% by 2035. 96% of this growth is projected to occur in developing countries. Most of the energy used in buildings is generated by burning fossil fuels. The energy pollution caused by buildings is often not obvious because it is removed from the point of use. For example, electricity often comes from coal plants with high GHG and particulate emissions. Their distant location shields consumers from some pollution but also makes them inefficient. In fact, 2/3 of the energy in coal is lost in generation, transmission, and distribution before it reaches consumer. A large portion of the energy received at a building is further wasted due to inefficiencies within a building. A greenhouse gas, sometimes abbreviated GHG, is a gas that absorbs and emits radiant energy within the thermal infrared range, causing the greenhouse effect. The primary greenhouse gases in Earth's atmosphere are water vapor, H2O, carbon dioxide, CO2, methane, CH4, nitrous oxide, N2O, and ozone, O3. Burning fossil fuels to generate energy creates greenhouse gas, GHG, emissions which contribute to climate change. Climate change threatens to roll back years of development advances as agricultural yields fall, diseases rise, and extreme weather destroys homes and livelihoods. Buildings generate nearly 39% of annual global greenhouse gas, GHG, emissions, see graph below. Water use in buildings. Buildings consume 25% of fresh water globally. Global water consumption has grown at more than twice the rate of population increases in the last century. In developing countries, this will increase by another 50% by 2025. At the same time, climate change will disrupt precipitation patterns. Over-extraction of water and its inefficient consumption in buildings is a serious concern. In the next 5 years, 2/3 of the world's population could live under water stress conditions. 1.8 billion people will be living in countries or regions with absolute water scarcity. Material use in building construction. The building construction industry consumes 40% of the natural materials entering the global economy. The graph below illustrates how the building construction sector dominates the consumption of a wide range of materials globally. For example, 75% of all concrete manufactured annually is used in buildings. Manufacturing materials is energy intensive and causes pollution. Reducing GHG emissions from building material production, otherwise known as embodied carbon, is critical to mitigate climate change. Embodied carbon is the carbon footprint of a material. It considers how many greenhouse gases, GHGs, are released throughout the supply chain and is often measured from cradle to factory, gate, or cradle to site of use. Green building design must consider embodied carbon in materials. The energy consumed in the production of a material is its embodied energy, and the associated GHG emissions are its embodied carbon. As energy efficiency in operations increases, embodied carbon in materials becomes a more significant portion of total GHG emissions caused by buildings. The figure below illustrates the energy use of an office building in Delhi over a life cycle of 25 years. The proportion of operational to embodied energy will vary depending on the context. In the materials module, we will learn how to calculate embodied energy in a building and how it varies based on its shape and specifications. A new vision. We need a new vision for our increasingly urban future. Conventional modern design is hurtling the world towards global warming. Vernacular design offers valuable lessons, but it struggles to fit into today's context. The need for faster construction, change in lifestyle, and the premium placed on urban land are limiting the adoption of past ideas. New solutions must serve the needs of the majority, who are most likely to be living and working in a dense reality surrounded by urban heat islands with dust, noise, and pollution. We have a small window of opportunity to shape our built environment. The compounding factors of resource crunch, rapid urbanization, and climate change are creating a perfect storm. The current speed of urbanization is difficult to grasp, and we have just a couple of decades before business as usual locks us into inefficient buildings that harm rather than help. These decades will be a blink of the eye relative to the length of human history. In the next section, we will uncover how we can navigate our way through this perfect storm and develop a vision for the future. Green building. Defining green buildings. Green buildings deliver environmental benefits through resource efficiency. Green is a relative term, in the sense that green buildings are simply more resource efficient than conventional designs. While there is no single definition of a green building, the defining feature is a significant reduction in environmental impact by reducing consumption of materials, water and energy, reducing air, water and land pollution, reducing disturbance to the local ecology and biodiversity. Green design can typically reduce energy use, carbon emissions, water use, and materials by 20%–80%. According to the World Bank, a green building is a building that uses 20% less energy, water and embodied energy in materials compared to an equivalent local benchmark. While a designer may not be able to influence the choice of location or the operations of a building, the designer does control the core elements, passive design features, material specifications, that make a building green. This course focuses on factors within the designer's sphere of influence. Benefits of green buildings. Green buildings deliver value in different ways. They are economically more attractive, and they put less burden on natural resources and public infrastructure. 1. They reduce pressure on infrastructure. 2. They preserve natural resources for longer. 3. They cost less to operate. 4. They command premium prices and improved rents. Green buildings have greater commercial value. Green buildings have higher sales prices, quicker sales cycles, lower operational costs, lower loan default rates, and higher resale values. Why are green buildings not mainstream? 1. There is a persistent perception among developers of costs higher than the evolved market reality. 2. Owners are hesitant to pay more upfront for uncertain future saving. 3. Banks are hesitant to invest in non-mainstream solutions. EdDG. Excellence in design for greater efficiencies. Government regulations are not aligned with the uptake of green building. Opportunities in green buildings vary by sector. A variety of technologies are available for different building sectors, with many variables to consider. The choice of green technologies can influence the building design. Residential sector. Domestic properties can be broadly split into single-family homes and multifamily properties. Each has differing design issues. However, when considering operational energy, the issues of thermal comfort, hot water and appliances are the main ones to tackle. Meanwhile, building material choices affect embodied carbon and other environmental impacts. High-impact interventions in the residential sector include roof and wall insulation, solar hot water heaters, water-efficient fittings and rainwater collection, smart meters for better control and metering, and low environmental impact building material. Commercial office sector. Tenant demand is an important factor for commercial office space. A well-designed office building can reduce operating costs significantly and provide future-proofing against obsolescence. Green certification boosts occupancy rates. Enhanced employee productivity due to better interior environment is also important for tenants but is not be covered in this introductory course. High-impact interventions in the commercial office sector include passive cooling and ventilation design, daylighting, lighting control and low-energy lighting. High-efficiency chillers such as ground-source heat pumps and solar PVs on the roof could generate significant energy. Healthcare sector. Hospitals and clinic operations are resource-intensive due to the importance of comfort and hygiene for patients. Building systems, therefore, become the main focus. The challenge is to reduce energy and water use in these facilities while ensuring that patient outcomes are enhanced. High-impact interventions in the healthcare sector include insulated and shaded facade, smart controls for lighting, variable frequency drives and ventilation heat recovery, and trigeneration using absorption chiller. Education sector. Educational buildings ventilation, views, indoor environmental quality and acoustics are all important issues. University buildings are often ambitious in terms of sustainability due to their potential both as a learning opportunity and for reputational enhancement. EdDG. Excellence in design for greater efficiencies. High-impact interventions in the education sector include daylighting, lighting control and low-energy lighting, external louvres to minimize glare, passive cooling of classrooms for thermal comfort, and on-site renewables such as PVs and wind turbines serve as an educational tool. Retail sector. Stores and malls are huge spaces to heat, cool and light to optimize the customer experience and promote sales. Much can be done with control systems and advanced technologies such as rooftop solar PV, but passive architectural design and daylighting is also powerful. Location and the propensity to trigger private vehicle trips is also a big factor in GHG emissions but will not be the focus of this course. High-impact interventions in the retail sector include daylighting and low-energy lighting solutions, passive or low-carbon cooling options such as displacement ventilation. Waterless urinals not only save water, they ensure drier floors and improve hygiene, and renewables such as PVs on the roof and wind turbines in the car park. Supermarket subsector. Supermarkets consume a lot of resources in refrigeration and lighting, and hence this is a priority for efficiency improvement. Nevertheless, the size and layout of sites also offer opportunities. The best solutions vary according to local climatic conditions. High-impact interventions in the supermarket subsector include low-energy lighting and daylighting, efficient refrigeration equipment and heat recovery, use of refrigerants with low global warming potential in systems which minimize leakage, and high-efficiency chillers. Hotel sector. Hotels present substantial challenges and opportunities for sustainability. On the one hand, resource use is high and therefore also the potential for operational saving. On the other hand, the guest experience cannot be compromised. Encouragingly, guests are becoming increasingly sensitive to sustainability. The rise of highly efficient eco-tourism hotels is just one sign of this. High-impact interventions in the hotel sector include shaded and openable windows, auto switch-off AC and lighting, solar water heating, and treatment and reuse of wastewater from showers and laundry. The principal rule for energy efficiency remains constant. Overall, for all sectors, the principal rule to achieve energy efficiency is to start with good design to reduce the need for electricity and fossil fuels. Those should be the last option after all options. Good design, improved operations, and renewable resources have been exhausted. Passive design is design that takes advantage of the climate to maintain a comfortable temperature range in the home. Passive design reduces or eliminates the need for auxiliary heating or cooling, which accounts for about 40%, or much more in some climates, of energy use in the average Australian home. On-site renewable energy generation can produce significant energy, environmental, and economic benefits by helping local governments and communities reduce emissions of GHGs and other pollutants. The green design principle of sequencing the design correctly should guide every decision. Calculation of resource efficiency matrices using the EdDG software. The EdDG Building Design Software. EdDG is an innovation of IFC, the private sector arm of the World Bank. EdDG is a green buildings platform that includes a free building design software, a green building standard, and a certification program. For the purposes of this course, we will focus on the design software aspect of EdDG. EdDG provides predictive modeling and analysis to help design green buildings at the lowest cost from the concept stage. EdDG empowers the discovery of technical solutions to reduce operational expenses and environmental impact without the need for detailed energy modeling. EdDG also instantaneously estimates approximate financial costs and benefits of solutions. In this way, EdDG allows designers to quickly identify the lowest cost, highest impact suite of solutions that work for their building, and also gives commercial decision makers the information they need fast. Comparing standard and improved building design in EdDG creates two cases, a base case and an improved case, for each project. The improved case is described in terms of the percentage of savings in energy, water, and embodied energy in materials which it represents relative to the base case. The base case in each city is determined according to current building practices, or the local green building code if it is being enforced. EdDG takes into account location-specific climate conditions, building type, customary occupancy and use, design parameters, and building orientation to create each base case. EdDG creates each base case by combining locally calibrated assumptions with project-specific data. Once the users have created the base case with building-specific data, they can select efficiency measures for energy, water, and materials to create the improved case. Virtual energy in EdDG. Virtual energy appears on the energy bar chart in EdDG when a cooling or heating system is not installed in the building. Virtual energy is the amount of energy that would be used theoretically to reach defined comfort conditions. Reduction in virtual energy will be reflected in energy bills only if heating or cooling systems are later installed. However, an occupant will immediately enjoy greater thermal comfort if a building is designed to reduce virtual energy for comfort, for instance by decreasing thermal gain through better shading. The chart shows virtual energy for comfort values for base case and improved case for a fully naturally ventilated building. Accessing the EdDG software, hover over an element in the software and a pop-up will provide contextual help. You now know the fundamentals of EdDG to get started. We will now go to the EdDG application and create our first building. This task carries 3 points out of 100. Creating a reference building in EdDG. Step-by-step instructions are provided here for EdDG v2.1. After completing these steps in the EdDG application, we will come back here to continue. Note that we will use the same building to perform exercises in later modules. So, care should be taken to create the building as instructed below.